So, hi, I'm Rabimbo. I have been trained as an engineer. I hope to say the same thing that I have been trained as a computer scientist by next year this time. And I take this problem of mitigation of hallucinations as a computer science problem. And what better it is to look at a data which is more relevant and which is very influential for this kind of task, which is health data. So today we are going to talk about what we can do to mitigate some of the hallucinations, how to come up with a proper framework and proper evaluation of are we actually mitigating them, and come up with a systematic way of verifying our results of this framework. So this is a work between me and my collaborator, Shurabhi Mojumdar, who is here from UT Health Houston. So let's get into it. First, as we have seen till now, almost all of the talks, foundation medical LLMs are kind of creating new opportunities for various health tasks. This is a chart I took from Google's MedPalm knowledge exams. This was just discussed before this that, okay, this has been starting to pass medical exams. So this is kind of like what they reported, how MedPalm works, and comparison between different other medical data trained LLMs. Now, that's all good and fine, and it's passing the exam, so which is also good and fine. How do we trust any of the result coming out of any of these LLMs? Imagine all the talks you have heard till now, how do you trust the data? So hallucinations are kind of a real thing, and as we saw from the panel discussion, they are part of the design. They're not a bug, they're a feature. But that's a feature we don't want in all of our use cases. So these are a couple of screenshots I took from existing studies, Google Cloud's own explanation why and how hallucinations occur, and is it good for our use case? Probably not, and probably not good for a lot of fact-based use cases. So let's look at how LLMs are working and how we can kind of mitigate these kind of problems. So very simple or very straightforward solution is that take LLM which is trained on individual level data. For us, this individual level data can be patient data. This concept is not new. How many of you have, in maybe past 1 week, have shopped in Amazon or anywhere else, or mostly like e-shopping carts? So, and if you have watched Netflix or Prime or any kind of these platforms, the concept is really not new or different. They all kind of use or build your user profile, and based on that, you get recommendation. That's a very simple recommendation system. Can we not do that for medical data? Can we not build individualized patient profiles and base our whatever prediction, disease prediction, or even any kind of other predictions based on those patient data specifically, not a whole large swath of everything? So a very simple conceptual thing will be that, okay, train your generalized foundational model and then ground your data. You have heard this term come a couple of times in last few talks because all of us kind of work in reducing hallucinations. So one of the popular approaches right now is grounding your data. What do we mean by grounding is that, okay, do not let your LLM answer anything apart from the data it's been trained on or it's been working on. Now, what we are going to show in this work in progress is that we are working with biobank data, and we want to eventually include a lot of other existing works which have worked with EHR data, more specifically Stanford EHR data, but that's a work in progress. But what I'm going to show today is mostly based on biobank data. So what does a biobank data have? So it has self-repo status of general practitioner nodes, hospitalization nodes, lab values, waveform data, imaging data. Something interesting is that if you see, these are not same kind of data. They're image-based, they can be audio-based, they can be time series, they can be just normal or textual data. So a very naive approach will be take your large language model and encode those data as text. Since most of the LLMs kind of work as textual souped-up prediction engine, why don't we pass that text inside the LLM as maybe in context, or just pass it through something like RAG? So if you do that, we kind of like tried with the approaches on the right. So when we say zero shot, it's like just asking your ChatGPT that, okay, this is the case, what do you think? Or what should be the thing? And in few shot, we give them like a couple of examples for our test, like evaluation test case. It's like 10 examples for each of the query. And we ask it, this is your test example set. Based on this, can you tell me this? Or based on this, what's your prediction? That's our few shot approach. And then something which is kind of like coming from the computer sciences code generation paradigm is fine-tuning, but prefix fine-tuning. So we kind of fine-tune LLM prompts prefixes, and here we do kind of a much bigger data set, for example, 10,000 for us, and try to see if it works or not. That's just using the LLM, not doing anything with the architecture. Good enough. But if you see, that's not exactly encouraging. So encoding the data in textual representation alone is not sufficiently strong for the performance. And we're not even going to the hallucination part yet. So for our input feature, if we have like 14 clinical and wellness features from biobank data, and we did a zero shot and few shot, and with soft prompting, if you look at the like graphs and everything, you will see this is not even comparable to the statistical methods we already had. That's like very few improvement, and times it's even not even improvement. So we need something more, and we also need to cater for other modalities. So how about encoding patient features? Here we come a little bit into the personalization. So we add the age, sex, BMI, and a data modality. For diabetes, we have certain clinical values. We pass it into the language model directly in the token emitting space, and then we ask it a probability that, okay, what do you think? Is it like, is this patient more diabetic or can be diabetic or not? And then we predict the disease risk. Now you will see that when we map these features into tokens, our model starts performing better than the traditional models. And these are a couple of data which the model has seen. So we have passed these examples into the mapping feature and asked the model, of course we did it like training and evaluation data set, and we asked it that, okay, is it like, does this patient has chance of depression? Does this patient has chance of myocardial infarction or stroke? Now, what about unseen traits? So we evaluated on 5 unseen like binary traits, and we see the model still performs, not as well as some of the other models, like statistical methods, for all of the diseases, but these are the traits the model has not seen. So we wanted to see, can it kind of like, based on the previous context, what it has seen for individual patients, can it also predict for unseen binary traits? Now comes the interesting part. That was all good and enough, but can we support multiple modality? Can we support images? Can we support time series data? More time series specifically will go into that. So what we did was that, take the same concept. Since we are anyway embedding that as a in the token space, why can't we embed multiple modalities? So what we do is that we start adding multiple modalities, which is spirometry and clinical values of something else. For us, we have clinical values for predicting asthma. So the green one is actually a tabular data, so we just parse that data, and for spirometry, we use prior existing work, their open source, like open data set, and we kind of like just pass them and see that, okay, can it predict or not? So this framework is able to handle multiple modalities, and more specifically, we are interested because it can handle time series data set. Now, what does it mean? So this is an example that if we pass multiple modalities and we ask something like that. You are conducting a survey, to determine if a participant has any disease, and based on your existing, what you know about your participants, you have this percent chance of having asthma. Based on that, what should you ask those patients? Very generalized use case. So if you, on the right, if you ask it that same question, and instead of P%, I gave a like 25%, and it gives me not, so you can actually try it with ChatGPT right now, or even Google's Gemini. What you see is that it will ask you normal questions, which people should be asking, that, okay, do you have history of asthma, like do you have been diagnosed by asthma by doctor? But then also it goes into not your symptoms, but also kind of like, yeah, on the third question, kind of like background, that, okay, did your family, does it come from family? Because it now knows from the data that it can be a genetic, it can come from the family traits. These questions are normally not going to come if you just use normal LLMs. This will probably come in their whole candidate questions, but not in the top questions. That's all good and fine, but we want to do more. We want to do personalized, and we also want to be sure that whatever we are asking, whatever data we have, we can actually go back and inspect from where it's providing those suggestions. So this is kind of like architecture we're playing with. So we want to encode sequential patient data and interactions. By interactions, imagine all the EHR records. They essentially can have time endings. So it has an interaction when they were first admitted to the ER, when the questions were asked, and then if we have more data down the line. Can we add all of them and build personalized profiles based on that? So what it does is that we have an autoregressive encoder for each of the patients or each of the data sets. And we use cross entropy to add it to the LLM and then the transformer stack, and then start asking questions. Some of the future work is, these are all the existing work which people have already done on EHR data sets. And we want to kind of start evaluating, because these data sets are available and we already have this data. So we want to start evaluating and see how our model performs, good or bad, with these existing data set. One other thing I wanted to, one other thing I wanted to tell is that with this, we also have a part where we have a small model called True NLI. What actually does is that once we have a result, each actually literally goes back and sees that it gives a prediction that, okay, this result is acceptable or not. What it has been trained on is that it gives you a citation score based on exactly if it can find anything on the data set it has been trained on. How it works in very short is that we have a huge data set, and we do what essentially RAG does. We use build a vector database. In very short, we do a semantic similarity search based on the data we have. And when we do a locality sensitive hashing, which gives us clusters of the data, which we map with the output. If the map is after a certain threshold, then we can say with high degree of confidence that, okay, most of these are coming from their data set, so yes, this is from our data set. If it is not, the model might be making it up. So even if it might be correct, we will not accept that result. So that's more or less what I had for today. These models these are essentially not using any GPT or any kind of commercial API. We are using Google's Gemma and PalyGemma kind of to do that. We also have a similar, we also have another work which works on, which uses image data, more specifically histopathology data. We have a poster based on that today in the evening, which utilizes some part of this pipeline to generate citations based on the results that one has. So these are our collaborators. Dr. Shi is my advisor, and I also work with Dr. Amin Alipur, mostly on code reasoning. My work is mostly reasoning part. And also Dr. Surabhi Majumdar, mostly for the health data. A lot of these works have been done with generosity from Google, who we collaborate with for the training parts. And thank you. If you have any questions, I'll be here, and I'll also be in the poster presentation. Thank you.